Welcome to the course of Electrical Circuits and Techniques. So it starts with the KCL and KVL, independent and dependent sources and their interconnection, power calculations, and the network analysis and the network theorems. So first we'll start with the basic network characteristics or the basic network elements. When you are saying the network consists of active and the passive elements. We are going to discuss over here. Those are the networks consist of only the RLC components and the sources. The sources might be dependent or independent sources and the RLC components. Now we'll first come across the sources. When you are saying the sources are of two types: voltage source and the current source. The sources as classified into basically two types, voltage source and current source. The voltage source is further classified as dependent voltage source and independent voltage source. Similarly, the current sources are also classified as independent current source and dependent current source. These are already shown in the figure. Now we'll first start our discussion with the independent sources. When you are saying the independent voltage source, in case of ideal voltage source, the potential across the source remains constant irrespective of the load applied across it. The voltage source may be open circuited or any amount of load impedance is connected across it. The potential across the voltage source remains constant irrespective of the load current, which is already shown in the figure. The thick line shows the characteristics of the ideal voltage source. Voltage always remains constant with the varying load current. But in case of practical voltage source, with the increase in load current, as the load resistance decreases, load current increases, which will have a loading effect on the voltage source, and with the increase in load current, voltage practically goes on decreases. It no longer always remains constant, which is shown by the dotted line in the figure. Similarly, we will have a discussion on independent current source. The ideal current source will always maintain a constant current passing through it, irrespective of the load resistance connected across it. With the increase in load resistance, the voltage across it increases, but the current given by the source always remains constant for ideal current source. But in case of practical current source, it is not able to provide the large amount of power. In that case, practically with the increase in load resistance, the load current goes on decreases. So it is already shown in the figure. The thick line indicates the nature of the ideal current source and the dotted line indicates the nature of practical current source. The figure shows the load current versus load voltage. Now, when you are discussing these current and voltage sources, the voltage or the current source may be time invariant or the time variant sources. Those are nothing but we can say these are AC or DC sources. Time invariant is DC and time variant is AC. Now when you are saying voltage source might be AC or a DC. It is shown by the symbol as shown in the figure. A voltage source, AC voltage source is shown with the sinusoidal symbol inside the circle, and a DC voltage source is shown with the fixed polarities inside the circle. Similarly, current source also of DC or AC current source. The current source, DC current source, is shown by a symbol with a circle and an arrow inside it. The arrow indicates the direction of current given by the current source. That is a DC current source. Whereas in case of AC current source, along with the arrow, a sinusoidal symbol is shown. That is AC current source. Now this is about the independent voltage and the current sources. Similarly, the source may be the dependent source. So when you are saying the dependent sources are of two types: dependent voltage source and the dependent current source. These two different types are further classified in two further. Like a dependent voltage source can be classified as voltage dependent voltage source and the current dependent voltage source. And dependent current source is classified as voltage dependent or current dependent. Means in case of dependent voltage source, the voltage may depends on voltage at somewhere inside the network or current at somewhere inside the network. Based on these are voltage dependent or current dependent. We'll discuss first voltage dependent voltage source. The symbol is shown in the figure where the polarities are shown, and V is equals to given as kV1. So V is the potential of the voltage dependent voltage source, shown by the letters V, D, V, S, where potential V is K times V1. So means potential depends on voltage V1 somewhere inside the network. Similarly, current dependent voltage source, the voltage of the source depends on current somewhere inside the network. That is, V is given as K into I1, where I1 is the current flowing inside the network at some point. Similarly, the current sources are also divided into two types: voltage dependent current source and the current dependent current source. In case of voltage dependent current source, the value of current source depends on potential at some point inside the network, that is I is equals to kV1. Whereas in current dependent voltage source, current of the source depends on current somewhere inside the network, that is current of the source I is K times I1, where I1 is current somewhere inside the network. So these are all about the dependent and the independent sources. Now when you are dealing with the network simplifications, that time number of sources may lies inside the network. We may come across a situation where number of sources either might be connected in series or parallel. So we'll discuss about the combination of sources and how to deal with it. We'll consider first your voltage source. Now we'll consider the series and parallel combination of voltage source. First we'll start with the series combination of voltage sources. So a figure shows the three voltage sources connected in series. Those are V1, V2 and V3. If you look at the figure, the polarities of V1, V2 and V3 are such that a negative terminal of every previous source is connected to the positive terminal of the next source. So in this series combination of the sources, as the polarities are directed in the same direction, the equivalent voltage source will have the polarity as algebraic sum of all the potentials or all the value of voltage sources. So potential of the equivalent source V is V1 plus V2 plus V3. Now let's suppose these voltage sources are non-ideal, having internal resistances R1, R2 and R3. Then this equivalent voltage source will have an internal resistance as algebraic sum of internal resistances of all the sources. That is, R is nothing but R1 plus R2 plus R3. Now we'll change this series combination slightly in the second part of the figure. Again the same three sources are shown, but now the potential source V2 is connected in the opposite sense. Now negative terminal of V1 is connected to the negative of V2 and positive of V2 is connected to the positive of V3. Now in such cases, the polarity of the voltage source V2 is opposing V1 and V2. It tried to pass the current in the opposite sense as compared to V1 and V3. That's why potential of V2 is opposing. So the equivalent voltage source will have a total potential as V1, then V2 is opposing, that's why it is minus V2 plus V3. So total potential is not algebraic sum. Now either we need to add or subtract, it depends on how the sources are connected. If all the sources are contributing in the same directions, potentials are added. But if the source is contributing in opposite direction, the potential is subtracted. But the net equivalent internal resistance remains unchanged. You might connect the sources in any sense. But in the second combination also, internal resistance is R1 plus R2 plus R3 only. Now we'll have a second one, parallel combination of voltage sources. The one thing is there, when you are connecting the voltage sources in parallel, we cannot connect the two voltage source of different potentials in parallel. Always two voltage source of the same potentials are connected in parallel. Like an example, you might have seen the UPS rack, where number of batteries are there used, which are either connected in series or in parallel. But what you will find, all the batteries are identical, because when you are going to connect them in parallel, all the sources must be identical. Let an example go through the figure, where the two potential sources V1 and V2 are connected in parallel, and the equivalent voltage source will again have the same potential as that of V1 and V2, such that V is equals to V1 equals to V2. V1 and V2 cannot be different in case of parallel combination. Whereas the effect on internal resistance, in parallel combination, net internal resistance decreases, because net internal resistance is parallel combination of internal resistances of V1 and V2. Then what is the use of connecting the sources in parallel? Potential remains same, but the current capability increases. In case of parallel combination, the net current given by the two sources is IL, which is a combination of I1 and I2. So net current capacity